Find two power series solutions to this given differential equation about the point x not equals 0. Okay, the coefficient of y double prime is 1 and which is never 0. So this x not equals 0 does not make this coefficient 0. That means 0 is an ordinary point. In that case, we can assume the following series solution for this. Okay, so let y equals some a n x n from 0 through infinity be a solution. Now we want to plug this into this ODE. For we need to find y prime and y double prime. Then derivative is n a n x n minus 1, just the power rule. Derivative of x n is n x n minus 1. Now we cannot start from 0. We can, but this makes the very first term 0. So 1 through infinity, and y double prime, do the derivative one more time. This comes to the front. So n minus 1 a n x n minus 2. Now n starts from 2 to infinity. If we write 1, then 1 minus 1 0. The first term would be 0, so just 2. Now plug these into the ordinary differential equation, ODE. So y double prime is here, so that's n minus 1 a n x raised to n minus 2, n from 2 to infinity, minus x times y prime. So we want to multiply this by x. So times x means x raised to n minus 1 times x raised to 1. So just xn. So this will be then n from 1 through infinity n a n x n minus y. Y is here. N from 0 through infinity a n x n equals 0. Now we want to combine these three series. Okay, this is xn, good. This is also xn. Now we have to make this xn. This is n minus 2, so add 2, 2, 2, 2, then subtract 2 here. So this becomes n from now 0 through infinity n plus 2 n plus 1 a n plus 2 and x n minus, let's write this, n from 1 through infinity n a n x n minus n from 0 through infinity, pretty much copying these two series, equals 0. Now we can combine these three, but the problem is this starts from 0, this from 0. These two are good, but this starts from 1. We cannot go back, but we can go forward. So let's evaluate this for n equals 0, then the remaining sum starts from n equals 1. Same thing here. So evaluate the first series for n equals 0. We get 0 plus 2, just 2 times 0 plus 1, 1 times a 0 plus 2, a2, and x0, that's 1. And here let's do the same thing, evaluate this series for n equals 0. So minus sign, a0 x0, x0 is 1, so a0. Now this sum is from n equals 1, this is already n equals 1, and this is also n from 1. These are all constants, plus the remaining sum 1 through infinity of everything here, xn, 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 xn equals 0. Here we got n plus 2 times quantity n plus 1 a n plus 2 minus n a n minus a n. Oh, we can combine these two, minus n a n minus a n. We can factor a n out, minus a n out, n plus 1. Okay, So let's do that, and let's simplify this. So this is 2a2 minus a naught plus here n from 1 through infinity, and now this is n minus a n out, n plus 1, and we can factor n plus 1, or let me write this, n plus 2 n plus 1 a n plus 2 minus a n out n plus 1 a n. If you distribute this negative and a n, you get this, all x n equals 0. Now we want to equate the coefficients of both sides. We are saying the whole thing is 0. That implies this constant 2a2 minus a naught is 0, and these coefficients for n equal to bigger than 1 is also 0. This whole coefficient is 0. So, and n plus 2 n plus 1 a n plus 2 minus n plus 1 a n equals 0, and this is true for n bigger than equal to 1. Look at the sum, and from the first we always solve for bigger index, so a2. Okay, that implies a2 equals, move this over, negative a naught to the other side, a naught over 2, and let's solve for a n plus 2. A n plus 2 is equal to, move this over, so negative becomes positive, n plus 1 a n, and divide by n plus 2 n plus 1, and n plus 1 cancel once we divide, a n over n plus 2, n bigger than equal to 1, and this is called recurrence relation. Okay, recurrence relation. Now we can find two solutions. Okay, and those two solutions will be linearly independent, by the way, and they form a fundamental set of solutions. And when we write down two solutions, we'll have two arbitrary constants, in our case a naught, the very first constant a naught, and a1. So we can simplify in the following way. For the first solution, let me write in this way. For the first solution y1, we set very first constant a naught is 1, and second constant a1 equals 0. Okay, and we get, this is only in the case when we are solving, when we are finding the solutions about an ordinary point. For a singular point, we cannot do this. Okay, so a naught is 1. Let's find all the constants, a naught, a1, a2, a3, and try to generalize. a1 we assume 0, a2 is given, in fact found here, a2 is a naught over 2, and we've assumed a naught is 1, so this is 1/2. Now a3 is given from this recurrence relation. Okay, when we take n equals 1, okay, n equals 1 in the recurrence relation, we get a3. a3 is now a1 over 3, and a1 is 0, so this is 0. By the way, a1 0, a3 0, and the gap between these two terms in this recurrence relation is 2. So the every other term, okay, every other term will be 0. a3 is 0. This implies, in fact, a5, a7, a5 will be dependent on a3. Since a3 is 0, a5 will be 0, and so on. a9 all 0. Okay, now let's find a4. We have to take n equals 2 in the recurrence relation. a4 is, in fact, so n equals 2, so a2 over 4, and a2 is found 1/2, so this will be 1/2 times 4, so 1 over 4 times 2. a5 will be 0. a6, so for we take n equals 4, a6 is a4 over 6, and a4 is found 1 over 4 times 2, and 6, so 6 times 4 times 2. looks like now we got the pattern, because a naught is 1 over 1, a2 is 1 over 2, a4 is 1 over 4 times 2, a6 is 1 over 6 4 2. Okay, then we'll write down the general term, and from there we find the solution. Let's try to write down a, these are look 2 4 6, so this should be 2n, then a 2n equals 1 over 6 6, so 2n, this will be 2n and 2 less, so 2n minus 2 times 2n minus 2, 2n minus 4 all the way to 4 times 2. Okay, this will be the a 2n, and this is true for n equals 1 2 3 4 etc. Okay, maybe for 0 as well. A0 is 1, by the way. Let's try to simplify and write this in nice form. So we can factor 2 from, we can get 2 from each factor. Okay, 2 times 1, 2 times 2, 2 times 3, all the way 2 times n. So this is same as 2, how many of them? There are n many, so 2 to the n. Okay, then that leaves n minus 1, n minus 2, all the way to 2 times 1. So it's like n minus 1, n minus 2, all the way to 2 1. That's just the n factorial. Okay, and this is true for n equals 1 2 3. Thus the first solution is y1 is, that was an x n, n from 0 through infinity. Okay, and which is, as we have all the odd a1 a3 a5 a7s are 0, we can write in this way: n from 0 to 4 etc, an xn to all the way to infinity, n equals 1 3 5 etc all the way to infinity, an xn. Okay, these are all in, we can separate into 2, and this is, by the way, 0. This part is gone, so we have this, and an means in fact a2n, because these are 2 4 2 times 0, 2 times 1, 2 times 2, and we have found this to be 1 over 2n. Okay, 1 over 2 raised to n, n factorial, and these are even, by the way, so not only x, and we have to write x raised to 2n. Okay, when we start from n through 0 through infinity, now I'm writing 0 1 2 3 all the way, this will be 2n. So this is a0 a2 a4, and that's a2n, so we put n equals 1 to 3, so xn should be x to the 2n. So this is the first solution, or this is a first solution. For a second solution, now y2, let's say y2, what we do is we set a naught 0, a1 1, and now we find a2 a3 from the recurrence relation. A2, if you go all the way, a2 was a naught over 2, that's a naught over 2, and we assumed a naught to be 0, so this is 0. So a4 will be dependent on a2, so a4 a6 a8 all of them are 0. Okay, let's find a3. For we need to plug in n equals 2 in the recurrence relation. What is the recurrence relation? Let me recall that. An plus 2 equals an over n plus 2. So the recurrence relation was an plus 2 equals an over n plus 2. Okay, I was wrong here, so we have to take n equals 1, and we get a3, so that will be then n equals 1, right? So a1 over 3, and a1 is 1 third. Okay, now n equals 3, we get a5, that's a3 over 5, and a3 is found in the previous step, so 1 over 5 times 3. Okay, and now n equals 5, we get a7, that's a5 over 7. A5 is 1 over 5 3, so 7 times 5 times 3. Now in this way these are all odd. Let's try to find the general term. A in this case 2n minus 1, or we want to start from 1, so n equals 0, maybe 2n plus 1. When n equals 0 we get a1. Okay, that will be then, this is 1 over, look, 7, we have 7, 2n plus 1. Now this is 2 less, so 2n minus 1 all the way to 5 3, or we can write always 1. Okay, let's try to simplify this. So if we want to write, and n is in fact in this case 0 1 2 3 etc. Okay, if we want to make factorial 2n plus 1 factorial, we are missing the middle terms, like 2n is missing here because this 2 less every single time, so 2n, so this is 2n plus 1 factorial, but we are missing 2n there, so we need to put 2n on the top. We are missing 2n minus 2 all the way to, we are missing 6 4 2, so 4 times 2. So if we multiply this on the top, we have to multiply on the bottom, so we get this. Next on the top, 2n plus 1 factorial, look, 2, we can factor 2 out, 2 2 2 2 2 all the way here, so see 2 times 1 2 times 2 2 times n minus 1 2 times n, so 2, how many of them? N of them. Okay, and that leaves n minus 1, because when 2 is factor, n minus 1 n minus 2 all the way 2 times 1. That's exactly the definition of n factorial, and this is true for n equals 0 1 2 3 etc. So this is the general term, thus a second solution, because we can always because we are dealing with homogeneous equation, and we can multiply a solution by any constant, get another solution. So second solution, y2 is again is same as a and xn, n from 0 through infinity, but we can do the following. We can put n equals, let's say 0, okay, 2 4 6 all the way to infinity, that's the even, an xn, and all the odds here, n from 1 3 5 etc. to infinity. Okay, now these are all evens, and these are 0 an xn, and we have here now some an's we just found, these odd, that's 2 raised to n factorial over 2n plus 1 factorial, and these are odd, so x raised to 2n plus 1. Then we can start from n equals 0 through infinity. Okay, final.